Wave equation is today's topic. Last time we have studied the following equation, which is shown in figure right here now, and explore its different parameters and define different variables visible in this equation. Ym, k, x, omega, t, and then we have seen what is stationary wave, what are the uh, what is interference, what type of interference are there. So now, what is wave equation? Basically, the wave equation is one of the most important equations in mechanics because it not only describes the movement of string and wires, also the movement of fluid surface, water, wave, etc. The wave equation is basically second order partial differential equation. There are so many equations in physics. Means, for example, Newton's second law can write it in the form of partial differential equation. Similarly, Schrodinger equation and other equations can also be written in the form of partial differential equation. Basically, we used to say that physics is the description of the second order linear differential equation. We will see how this linear differential equation is derived, and then what is the purpose of this equation, what is the importance of this equation. So before going into details of the wave equation, we will start from this diagram. What is this diagram is? What type of information is provided in this diagram? Basically, this diagram, this line, which is shown here from F1 to F2, this is basically a part of the string element, which is vibrating, which is in which we are producing wave. This is basically, we take an example of the string here, and uh, my enlarged figure of this small segment of string is shown here when wave just started to move on. I mean, when you just start the, if you are holding string with your one hand, and on the other side of the string is fixed with the ball, and you just start the your movement of your hands. So left side, right side means F2 side is towards the ball, and right side is toward is in your hand when you just start the movement. So it is almost a linear motion, just a small height, just a small fractionally uh, height side of the F2 is showing that wave is traveling in this right side. So, and length of this segment which we are considering is L, small l, and dx is the linear length, which is almost equal to almost, not exactly, almost equal to dx. So overall, acceleration, spring acceleration is in upward direction because wave is traveling forward. So it is overall acceleration is up in upward direction. The second diagram is showing the direction of the force. Definitely, force will have components. F, here is only F2 component are shown here, but similarly, to apply the same technique on the right side force as well. To start by resolving the force F2. First of all, we will resolve this equation, this equation for uh, F2 force. Then we apply the same technique on the F1. So here we will apply Newton's second law because this equation belongs to classical mechanics. In classical mechanics, Newton's second law is applied on every type of motion. So what are the requirements in Newton's second law? Applied force, applied force, then mass, and then acceleration. Only three things required in Newton's second law in order to apply Newton's second law. So mass is here is not given here. Why and then why net by force? Why not only force? So similarly, what is m? M is not given here. What is acceleration? We have to calculate the acceleration as well. So how to calculate the mass of the string is segments of the mass. Suppose we are given the density of the string element, that linear density mu. And you know what is density? Density is the mass per unit volume, mass per unit length, mass per unit area. What type of the density we are considering? Here we are talking about the linear density because string is considered to be in one-dimensional dimension, carrying one dimension. So we will talk about the consider the only linear density of the string, which will be mass per unit length, and which will remain constant for every length. Either you're taking one millimeter length, either you're taking 1 centimeter length of the string, either 1 meter or any length. Density of the string must be remain same throughout the length of the string. So here we are taking the very small part of the string. So we will say that mass of the small segment is dm rather than the mass. Small mass, m is the mass of total mass of the string, and dm is the mass of the small segment of the string. In which is visible to us in this diagram. So L is the length of the segment here. So because this is this incline in upward direction, this rise in upward direction is very small as compared to this one, this end F1 to F2. This is very small angle. So we will take that dm is approximately, dx is approximately equal to small l. So we put this equation into this one, dm is equal to mu dx. So this will be the equation for the mass of the string element. We will use it in the upcoming derivation. So up to here now, just remember this is the mass of this length segment of the string. And similarly, acceleration is only y is equal to d square y over dx, the second order differential equation. Means because it is derived from the displacement, y is the displacement in perpendicular direction of the string. So when we take the first derivative, it will provide you the velocity of the string element, and when you take it order second differential derivative, then it will give you the acceleration in the perpendicular direction of the string. And now, very important part is here is the calculation of the net force, which is here, first equation basically. First equation. What is the net force? There certainly there is a difference between these forces. Otherwise, it will not be moving in upward direction. So here F2 uh, is right side force and F1 is the on the left side force. So first we'll try to resolve the F2 force here. So we resolve the F2 force into components, mass component, this force, basically this component y into vertical and horizontal component F2y and F1y, F2x, sorry. So here slope of it is given. Apply the simple equation here, find the net force. What will be the F2 force? Because F2 force is such a force which has the tendency to move the string element in upward. We will write it in the form of tau, right? This is just a symbol here. It is may not be considered as the just with about the torque to produce the rotational effect when we apply some force. So rotational effect may be there, but not here. We are taking just as a symbolically giving the name of the torque of F2 force. But look at the carefully. If you see here, F2x is high, very much high in magnitude as compared to F2y. Because wave is traveling in horizontal direction. Very small displacement along y-axis as compared to. So here F2x is very much higher than the F2 component of the force. When we put this into this equation, we take the squares, it will further reduce. Small magnitude will further reduce when we take the square. We can here ignore it and consider that r just is equal to 2 pi F2x. Put this tau value into equation. This equation we have taken it as equation number, we have given the name F2. So now put into this equation. So earlier equation number 2 now we will come like this. Similarly, we will apply the same technique to resolve the equation number 1. You get the same result. But just now rather than F2y, we get F1y and tau F2. So these are the equations for the force. Resolve, we have not resolved the force. Find the force next. Basically, S1, S2 are the slopes of the strings on right hand and left hand. So because we talked about the net force, because there is a slight tilt in upward direction in the string. In this diagram, there is slight tilt in upward on the right side of the diagram. There is a slight tilt in upward direction. So that is where there will be that force will not be zero altogether here. So there will be some net force exist here. So this S2 minus S1 basically, and put the values of mass. This is basically mass. dm, and this is acceleration. This is net force. This is acceleration. So taking the common S2 tau from the left side of the equation, this equation now will become S2 minus S1 dx. So now we have put here, basically we simplify the equation and rearrange the equation dx to uh, come here in mu over tau is equal to d square y over dt square is the acceleration now. So this is the shape of the equation is now here. Right, left side is describing the displacement slope, change in slope with respect to distance, and right side now become the function of the time. So this is how time and displacement equalize with some certain constant. So slope are slightly different from each other as is defined as overall slope. So overall slope is become the ds over d. Now look at the equation, this equation. This is very now important equation, very interesting equation. Rate in change in slope of the stream. Rate in change in slope with respect to displacement. With the change in displacement along the x-axis, how much change occurred in the slope of the stream will determined by the time rate in change in the displacement along wire. The acceleration of the stream along wire. So how displacement is not changing into time. You put the value of s in this equation and hence because now you look at this equation number, this basically not number is not here in derivation. So dy over dx over dx. Now it is the basically d square y over dx square. It means on both sides of the equation. Now there are uh, second order differential involved now. We can write here instead of the complete differential d square over dt square or dx square because there are two different variables. Equation is there. This equation is not involve two different variables on two different on right side and left side of the equation. So we can write this equation into partial differential, the form of partial differential instead of the complete differential. So partial differential is always used in such conditions when both in the equation in one equation two different variables involved in the denominator. I mean we are taking the derivative with respect to different variable. I mean x and displacement and time are totally different identities. So we will take the instead of the complete differential, we take here the partial differential. So basically this variable mu over tau. If you will drive the dimensions of this term mu over tau, you will find that this is equal to the one. This is basically term is derived in our previous topic of the this chapter. This is the reciprocal of the square of the velocity. So now this is the standard wave equation, which is partial differential equation and involves the interchange of displacement into time. So this is our required general wave equation. So up to now, if you have any question, please raise your hand, ask the question. So let's say, sir, yes, sir, what do you want to ask?
सर जो लास्ट इक्वेशन में 1/v² आया है
जी जी।
उसमें v², v हमारे पास वेलोसिटी है या कोई और
नहीं
फैक्टर है?
नहीं, वेलोसिटी है, v इज द वेलोसिटी ऑफ दिस थिंग। तो ये बेसिकली,
ओके सर।
हाँ, ये प्रीवियस टॉपिक में ड्राइव्ड है। आप देख लो, बहुत सिंपल है डेरिवेशन इसकी। और आप इसकी डिमेंशन भी कैलकुलेट करके देखिए। म्यू की, म्यू क्या चीज़ है? डेंसिटी है ना। म्यू इज द डेंसिटी ऑफ दिस थिंग, राइट? एंड व्हाट इज that here? Is the force, right? You can turn into dimensions of the velocity as well, right? Anyone else? Yes, Saha, do you want to ask any question? Hello? So right now, and when you keep on vibrating this string in upward or downward direction, what will happen? One wave will be traveling in the left side and strike with the wall and will be reflected from the boundary. And now, if boundary is frictionless, then will not any occur loss of energy with this when wave interact with the wall. So what will happen? It will be reflected with the same frequency, with the same wavelength. So in such case, there is the probability that this type of movement produces stationary wave, as it happened in our experiments of measurement of frequency of AC main. But if the boundary is not fixed, sorry, string is not fixed with the wall, rather it has some loop with when wave travel along the string and strike with this boundary, and boundary of the string is not fixed there. So what happened basically, this string apply the force on this loop and it try to push the loop in upward direction, because what was happening earlier here, this wave is disturb the medium, transfer the energy on the left side. So it will have the tendency to move this open loop in upward direction. So it will, rather than reflecting the wave, reflecting back the wave, it will push upward direction, like in this third diagram, so third and fourth. So now, when it will go a maximum displacement amplitude from its mean position, no wave will be reflected. So in such case, when boundary is not fixed here, so no more stationary wave will be produced. It means not only the condition of the wave is important, rather than the condition of the boundary is also important to produce the stationary wave. So that is why uh, in our musical instruments, in our uh, some practical cases, when we observe our resonance in our sound. So this is one boundary is one of the reasons due to which we listen back our sound, and at some point there is a loud noise as compared, on the other point there is a less noise listening here. So it is just within 1 minute we know. So after the completion of this meeting, we will come back again and resume our class again, because in last week we have uh, we are unable to get complete the class. So now we will start after 5 to 7 minutes. We will start again. Okay. So please hold on, take a short break. Okay, goodbye.